computer. So I'm recording on the computer now. So question 38 now. Is this fine now? Cracked. I'm pointing on cracked now. Is the screen still lagging or not?
No, it's good now.
So okay. I didn't know that. So one molecule of dodecane is cracked, producing 3 molecules of X, Y, and Z. X is a straight chain alkane Y, and Z are straight chain alkenes with different MR values. Which statement would X, Y, and Z are correct? So this molecule is being cracked. C12, and it's being cracked into 3 things. So one of them is a straight chain alkanes, and Y and Z are alkenes. So a straight chain alkane would be CnH2n plus 2. And you've got 2 alkenes, and we'll put the numbers later in, but there are 2 of them and they have different MR values. So 2 of them are alkenes. Which statements about X and Y and Z are correct? If Y and Z are butadiene and ethene respectively, X will be hexane. So is that correct? What's X? C6H12?
Yes.
Butadiene, what's the formula? C4H8? And ethene is C2H4. So everything, it looks correct. Everything should add up to be this thing. Are the hydrogens adding up? That's 12 plus 8, 20. The hydrogens are not getting added up. Are they getting added? No, sorry, this would be 14. Sorry. See, this would be 14. So it's an alkane. So the first one is true. What about the second one? If X is butane, Y and Z could both show cis trans. So X is now butane, so that's C4H10. What are the possible formulas of the 2 alkenes? And can they both show cis trans? You're left with 8 carbons. So you can have a 5 carbon atom alkene. Can anyone answer this? Will both of the 2 remaining alkenes show cis trans? And it says
No.
What can the 2 remaining alkenes be? It's either because they have to have different MR values. So one of them will have 5 carbon atoms, and the other one will have 3 carbon atoms, right? What's 5, 9? So 12 carbon atoms. That's I said, can the 2 show cis trans? Which one will not be able to show cis trans? I mean, propene over here cannot show cis trans because with 3 carbon atoms, if you put a double bond, one of the carbons will have 2 H's and it will not be able to show cis trans. Is that clear? And remember the question had stated that both alkenes should have different MR values. So you're left with 8 carbon atoms after butane. So what else could you have? You can have 6 and 2, right? 6 carbon atom alkene. So this would become C6H12. And you can also have a 2 carbon atom alkene. Now again, the problem is that a 2 carbon atom alkene will not be able to show cis trans. The only way the 2 can show cis trans is if you have a 4 carbon atom alkene and you have another 4 carbon atom alkene. Because with 4 carbon atoms, you can show cis trans. Okay, so if you have this and you've got 4 carbon atoms, the double bond could be in the middle and it will show cis trans. But they had stated that both alkenes should have different MR values. So you can't do this. You can't have cis trans as well as Y and Z having different MR values. Is that part clear? Second one.
Yes.
Yes.
Yeah, so the last one is X is octane. Why is that wrong now? So if the first one is octane, why is that wrong?
Octane would be C8H, C8H18.
The octane is C8H18. I'm just saying.
The only possible alkenes would be C2 and C2H4, and they can't be
Okay,
of
so
same.
yeah. So the reason is that you're left with 4 carbon atoms, because if you crack this molecule over here, you've got C8H18, and you're left with 4 carbon atoms. And with 4 carbon atoms, you have to make 2 alkenes. So the only 2 possible alkenes would be C2H4 and C2H4. They can't be the same. Because remember, the smallest alkene has 2 carbon atoms. So you can't have 3 and 1, you can't have 1 and 3, because that's not possible. So that's the only possible one that's remaining, and he had clearly told us that they didn't have the same MR. So the last one is also going to be incorrect. Now moving to the previous one, we've got this question, and which statement about the reactions. Is the previous one clear to everyone?
Yes.
Yep.
So the next one is, we've got this acid. It's a compound with 2 ketone groups and 1 carboxylic acid group. Which statement about the reactions of limonene and this thing are correct? So there's another. So I don't know what this is. It's got 2 ketone groups and 1 carboxylic acid. When reacted with an excess of hydrogen and a nickel catalyst, both of them produce the same compound. Is that true? This is hydrogenation. You're adding hydrogen to it. Will these two produce the same compounds?
Yes.
Okay, well, because the double bonds will go away. You'll have hydrogens getting added over here, hydrogens getting added over here. So all the double bonds would go away. So the molecules would look exactly the same without the double bonds. So the first statement is correct. They'll look exactly the same if hydrogen gets added and the double bonds are removed. Now, in excess of hot concentrate, KMNO4 is added. And he says that it reacts with this first one and the second one to form different diketo acids. So is that true? So what will happen when you'll have strong oxygen?
Since the double bond at the end are different, so one of them will have ketone. The top ones would remain same.
As a one by one. This red one, just let me remove this first. 1 second.
It will make a ketone.
See, just a second. Let me get rid of the double bonds. I'm breaking the double bonds. The double bonds would completely break. So what about the first one? That's a ketone, right? Okay, so 2 carbon chains, that's a ketone. What about this other carbon atom, the one that I marked in red?
Carboxylic acid.
So that's carboxylic acid. 1 carbon chain, that's carboxylic acid. And what about this carbon over here?
Ketone.
Okay, so you're getting, and this one would be carbon dioxide and H2O, right? The single carbon atom that broke away. So you're saying, so a diketo acid, 2 ketone groups and a carboxylic acid. Got 2 ketone groups and a carboxylic acid. This one is true. What about this other one? That's a, what is that? That's a
ketone.
Okay, that's a ketone. This one is single carbon chain. That's carboxylic acid. What about this carbon atom over here?
Ketone.
Okay, and this other one is also a ketone, but that's a different molecule now. But you're getting a diketo acid as well. 2 ketones, 1 carboxylic acid. So it is forming that. So I guess this one, they're forming different diketo acids. They are different as well. They both look different. So that one is correct. A reaction of this thing with an excess of Br2 produces positional isomers with the same number of chiral carbon atoms. So we need to go back now, just a second. So let me. So now he's reacting it with Br2. So what will happen? The double bonds would go away. So imagine all the double bonds are gone. BRs are going to get added. This one would be a BR as well. There's going to be a BR that's added over here. Think of the double bonds are gone now. So BR and BR getting added, and now imagine the double bonds are not there. So produces positional isomers. Are these positional isomers of each other?
They're honestly the same.
Everything looks the same, but they are positional isomers because the BR position, isn't the BR position different? Like
Yes.
I mean,
Yes,
over
sir,
here,
at the end is different.
over here it's the same, but over here there's a BR that's over here and over here, but on this side it's positionally it's different, right? So they are positional isomers. And do they have the same number of chiral carbon atoms? How many chiral carbons are present in this molecule over here? Is this chiral, the first one?
Yes.
Okay, that's chiral. What about the second one over here? That's
Also chiral.
okay, because all four sides they appear to be different. There's going to be one H. What about this one, the one over here? Is this chiral?
Yes. No.
No, this one.
No.
This.
No, it's not chiral.
Isn't it chiral? Because this side is different. This side is different. The bottom side is different, and there's one H as well, which is not shown. So all four sides are different on this carbon atom. Is that clear? That is chiral. Remember, in cyclic compounds, if you travel from this side, if you travel from this side, both sides they appear to be different. This side has only carbon chain, this side has bromine on it. So the two sides are different. Is that clear?
Sir?
That Hanji?
सर आप सारे चेन्स को देख रहे हैं
क्या मतलब?
लाइक ये जो बीआर जो एंड पे अटैच है आप दोनों साइड्स पे चेक करें ना कि
But if you start traveling from this side, right? This is CH2, C with two H's. This is CH2. If you travel from the other side, you got a CH2, then you got a CH with a BR. So this side is different and this side is different. Is that clear?
Yes.
You are, even though they do connect at the other end, but the sides are different. On the right side, you have something else. On the left side, you've got something else. So this one is chiral. Is that clear? What about this next one? Is this chiral, this one? The one with BR?
Yes.
No.
That is, on the top, you got this whole thing. On the right side, you got this. On the left side, you got this, and there's one H as well. So all four sides are different. So that is chiral. This last one is not chiral because it's going to have two H's with it. Right. So the last one is not chiral. So you got four chirals. The fifth one is not chiral. What about this other one? How many chirals does this have? This is chiral, right? The top two are chiral. Imagine the double bond is gone because over here there's going to be an H as well. So all four things on this carbon atom are different. This one is going to be chiral as well. So we've got this one as chiral. And is this going to be chiral, the last one?
No.
Because this side and this side are the same. So the last statement, the positional isomer thing is correct, but they don't have the same number. I mean, they're definitely not having the same number of chiral carbon atoms. So the third one is wrong. Is that clear?
Yes, sir.
The third one is, you can double check, but the third one, definitely chiral. And somebody please open a marking scheme as well for this so that you can double check this. But the third one, half of it is true. The other half is wrong. Is that clear, this one?
Correct. B is the option.
Okay. Now, which statement about calcium oxide are correct? It can be reduced by heating with magnesium. Is that true? Will magnesium react with calcium oxide? Is there going to be a reaction? Who's more reactive, magnesium or calcium? Remember, more reactive.
Calcium.
It's calcium because reactivity increases down the group. in group 2. So magnesium will not be able to displace calcium. It won't do anything. So the first one is wrong. So is calcium oxide produced when calcium nitrate is heated? Is that true?
Yes.
Yeah,
Yes.
that's also true, and it will react with cold water, calcium oxide, because remember, calcium oxide, even in the notes, it's written that calcium oxide has a very vigorous exothermic reaction with water. When it forms calcium hydroxide, there's a lot of hissing produced because there's going to be a small lump of calcium oxide, which is white in color. You add a few drops of water to it, a lot of steam and a lot of heat is given off. There's a lot of cracking, and there's a lot of it's like I mean it's a lot of heat and steam is produced when you put water on calcium oxide. So the last two statements are correct. Which statement forms a chloride? Which elements forms a chloride in which both covalent bonding and coordinate bonding are present? So will aluminum form a chloride with both dative and it will, right?
Yes.
Because it forms a dative a dimer, right? AlCl3, it datively bonds with another AlCl3. Al has an incomplete octet. It has 6 electrons, so it borrows a pair of electrons from Cl and datively bonds with it. Cl has got a lot of lone pairs. So that is true. What about silicon and magnesium? Will they form covalent bonds and dative bonds in the same chloride? What is SiCl4? SiCl4 is purely a covalent molecule, that's it. Doesn't really, it's a tetrahedral covalent molecule, it's a
It does
liquid.
not have dative bond.
It doesn't form dative bonds. Silicon's outer shell is kind of complete. Mg forms ionic chlorides. It doesn't even form covalent bonding, so that is out of the question. Which molecule contains at least one unpaired electron?
NH3.
Unpaired. He's talking about unpaired. How would you know that a molecule has unpaired electrons? How many electrons would it have if it's got an unpaired electron? Like how many electrons in total will it have if it has unpaired electrons? Because remember, you don't know, even I don't know what is the structure of NO2. And I'll tell you, NO2 has a resonance structure which is not in your course. It's so you don't even know how how the bonding in NO2 works or in NO works. So the question is, how would you know if a molecule has unpaired electrons? How many total electrons would it have if it's got unpaired electrons?
7.
It's going to have an odd number of electrons. Like look at Cl. Cl has unpaired electrons, right? It's got 7 electrons. So the point is, you're going to have an unpaired electron when you have an odd number of electrons. Is that point clear? So when you have an odd number of electrons, that means you've got an unpaired electron. Otherwise, all of them would be paired if you have even number of electrons. So the first one, does it have an unpaired electron? N has 7 electrons, oxygen has 18 electrons. Sorry, not 18. Oxygen has 8 electrons, right? So
15.
In total, so it's
the total is
Yeah.
coming out to be odd. So that means it has at least one unpaired electron. What about NO2? It's got N has 7 electrons, oxygen has 8 electrons, and there are 2 of them, right?
1.
So again, there's going to be one unpaired, right? What about NH3 then?
It's not.
Because N has 7 electrons and hydrogen has 1 electron, and there are 3 of them. So that makes it a total of 10 electrons, and it's not going to be unpaired. So you can even draw the NH3 dot and cross diagram. And when you draw that, N has 5 electrons in its outer shell. All of them are paired. This is a bonding pair, bonding pair, bonding pair, and there's a lone pair. So all of them are paired. So that you don't have odd number of electrons. TK, is this point clear? This is important. TK, is that clear? You can write it down somewhere.
Yes.
We've got this question, ethylene glycol, that's this molecule is used as a deicer. It allows ice to melt at temperatures below 0 degrees centigrade. Which statements are correct? The ethylene glycol disrupts the extensive network of hydrogen bonding in ice. Can it do that? Like if you have 2 water molecules and those 2 water molecules are, I mean, the lone pair of oxygen is attracted to the positive H from the other water molecule. They're attracted to each other. Can ethylene glycol disrupt this? Like if I have O with H and I got a lone pair, can ethylene glycol disrupt the hydrogen bonding that is present? First thing, can it form hydrogen bonding in the first place?
Yes.
Yes, so it can form hydrogen bonds, right? So the H is positive. The lone pair has a pretty strong negative charge. So can it disrupt the hydrogen bonding? So instead of the water molecule that were getting attracted to each other, if you add ethylene glycol, the water molecule will be pulled out of the hydrogen bonding will get disrupted. Why? Because the water molecule will get attracted to ethylene glycol instead. Is that clear? So the force of attraction over here would become weaker because the lone pair over here will be pulled towards ethylene glycol. Is this clear that it does disrupt the extensive network of hydrogen bonds in ice?
Sir,
Yes.
so like at the same time, what hydrogen bonds to water can they be sugar? Exactly same hydrogen bonds water can they?
But
I
is
mean,
it disrupting? I mean, the point is it disrupting the hydrogen bonds that are present in ice? These two were bonded to each other, right? But once ethylene glycol comes in, ethylene glycol can also form hydrogen bonds. So instead of the water forming hydrogen bonds with each other, the water molecule will get attracted to ethylene glycol and it will start forming hydrogen bonds with ethylene glycol. So is the hydrogen bonding getting disrupted? It is getting disrupted, right?
yes.
Okay. But disrupt means that is it changing? It is changing. There's a change happening, right? So the next question is this part clear?
Yes.
As now the next one is you've got ethylene glycol molecules which form hydrogen bonds with other ethylene glycol molecules. Can they form hydrogen bonds with other? I mean, they can obviously, right? Ethylene glycol with other ethylene glycol. That's true. Ethylene glycol molecules will dissolve in water formed from the ice. Will it dissolve in water? Will ethylene glycol dissolve in water? I mean, it will dissolve with water, right? Because it can attract water. Is this clear? Like it's obviously going to mix with water because it's attracting water. So so remember, things that form hydrogen bonds will always dissolve in water. So the last all 3 statements are correct. Is this clear to everyone?
Sir?
Yes.
So what third polarity की वजह से ना like उसके पास charges ज़्यादा.
Because anything that forms hydrogen bonds will also mix with the other things that form hydrogen bonds. Similar type of attractive forces, they always mix because they always attract each other. Now this one, question 32, iron reacts with steam to produce hydrogen and oxide of iron. The system containing all 4 substances is this is at equilibrium. Which changes will decrease the mass of Fe present at equilibrium? So the mass of Fe present has to decrease, right? So decrease the mass of Fe. So the first one, addition of steam at constant pressure, will it decrease the mass of Fe?
It should be increasing the mass.
If you add steam, if you add more steam to it,
It will decrease because there is a gas which will escape.
Concentration will decrease.
It's simple that if you add something, it tries to remove that, right? If you add more of steam, the equilibrium would automatically shift to the right. Is that clear? I mean, if you add steam to it, more of it, the concentration of steam would increase and the equilibrium would try to decrease it. So it's going to shift to the right. What about increase?
But it will increase the mass, right, of Fe. Oh.
It will? Can you repeat?
I'm just confused. So you're saying that if we add steam, it will increase the mass of Fe.
It will decrease the mass of Fe. If you add steam to it, right, where would the equilibrium shift? I mean, the rule is that if you try to increase the concentration of a substance, the equilibrium will try to decrease that, right? So if you try to increase the concentration of steam, the equilibrium will shift forward so that the amount of steam decreases. And if it shifts forward, what happens to the mass of Fe? That will also decrease because a lot of Fe will get converted to Fe3O4. Is that clear? So the mass of Fe would also decrease simultaneously. Is that clear?
So the second is right.
As increase in overall pressure. So where would the equilibrium shift?
Right.
And what's the rule? Less gas, more gas?
Less moles.
Less moles, right?
But less gas moles, right?
Moles
So
are the same.
the moles of gas are the same. You got four. I mean, this is a solid. Okay, that doesn't count. Pressure only affects, it shifts to the less gas mole side. So you got 4 gas moles over here, you got 4 gas moles on this side as well. So nothing would happen. There's not going to be any. Hanji.
So you're not counting solids?
No, pressure, solids and liquids has nothing to do with pressure. Pressure is created by gases. And this rule, remember there's 3 rules. One is if you increase concentration, it tries to decrease and vice versa. The other one is if you increase pressure, the equilibrium will shift to the less gas mole side. And remember, you're not going to count solids and liquids, only less gas moles. So which side has less gas moles? No side has less gas moles.
They're equal.
And adding a catalyst will have no effect as well on the equilibrium position because both reactions will speed up equally. So the amount of Fe would remain exactly the same. Okay. I'm going to repeat the first one. The rule is if you increase the concentration of something, the equilibrium tries to decrease it. So if you add steam, the concentration of steam would be higher. The equilibrium will try to decrease it. How will it try to decrease it? It will move the equilibrium to the forward side. I'm talking about the first one. If you add steam, if you increase the concentration of steam, increase the amount of steam, the equilibrium will try to decrease the amount of steam. And it's going to do the opposite. So the only way it's going to do the opposite is by moving the equilibrium position to the right side. So when the equilibrium moves to the right, the amount of Fe would decrease because a lot of that will be converted into Fe3O4. So the amount of Fe will decrease. Chandik, is that clear? That's 31 now. We've got which changes can be used to measure the rates of chemical reactions. So remember, you're measuring the rates. What is rate? How quickly a change is happening with respect to time. So when you have a reaction, how do you measure speed? How quickly, and it could be any change. It could be a color change happening with respect to time. How quickly that happens. There might be a gas being produced. How quickly does the gas get produced? So a lot of things. So the decrease in concentration of a reactant per unit time, that is going to measure U rate because the concentration of the reactant will change when the reaction happens. So how quickly it happens with respect to time, that will give you the rate. The rate of appearance of a product, that will also tell you how quickly the reaction is happening. So if the appearance or the color changes very quickly, the reaction is fast. If it changes very slowly, the reaction is slow. The increase in total volume of gas per unit time, so that will also give you rate. So if there's a gas forming, and if it forms very quickly in a very small amount of time, that means the reaction is happening very, very quickly. Okay, is this part clear? And remember this thing, that you can measure any change as long as that thing is changing during the reaction. Like if there is
Can you repeat this entire thing?
It's just, I'm going to explain everything. Let's say I have a reaction, right? Mg with HCl. And it's forming MgCl2 plus H2 gas, right? The point is that how do you measure the speed of reaction? The speed of the reaction is how quickly something changes. So what is changing in this reaction? There are a number of things that are changing. For example, the solid is dissolving. So what you can do is You've put HCl, you've put a solid Mg into it, right? What you're going to do is you're going to start the stopwatch and you're going to time it. How quickly does the Mg dissolve? So maybe after 10 seconds, the Mg becomes invisible. So that is your change with respect to time. You can measure the time. The shorter the time, the faster the reaction. So it could be any change that is measured with respect to time. What else can you measure? You can measure the bubbles that are being produced. How quickly are the bubbles being formed? So the bubbles will start forming as soon as the reaction starts, and it will stop because H2 gas is being formed. So you can measure the bubbles. You can start a stopwatch, and you can see how quickly do the bubbles they vanish, because that's when the reaction stops. So that's another change that will happen during the reaction. At the beginning, there's going to be a lot of bubbles. At the end, the reaction ends, and there wouldn't be any bubbles. So you can stop and time how quickly that happens. You can also measure the volume of H2 gas and see how quickly that is formed. So any change with respect to time is basically a measurement of rate. Is that clear? Yes. So the concentration of the reactant decreasing, that will happen during a reaction, and you can measure how quickly that happens. The appearance of the product will also change. Sometimes it won't, sometimes it will, but when it is, you can measure how quickly the appearance of the product changes with respect to time. You can measure any changes in the volume of gas with respect to time. So any change can be measured with respect to time, and that will measure you the rate of the reaction. As moving to the previous one, does it have, so this one, it's a bigger question. The infrared spectrum of 3 organic compounds are shown. So which one is, what is this? 1700 strong absorption.
C double bond O.
Because this one just has C double bond O, no OH of any type, right? So just a C double bond O. We don't care about the others at the moment. You got another C double bond O over here as well, right? And you got a strong and broad absorption at 3000. What is that?
OH. OH.
But what OH? Like,
it's in the OH, the one spectrum too.
In the carboxylic acid. Yes, what's the question? I mean, I can open the data booklet, but I guess these three should be remembered, right? 1700, that's C double bond O. Broad absorption at 3000, that's a OH that belongs to the carboxylic acid. What about this one? Does it have a C double bond O?
No.
So there is no C double bond O, and but it's got an OH. It's got an OH, and it's not at 3000, above 3400, 3500. That's a normal OH. That's an OH that belongs to an alcohol. So there's no strong and broad absorption at 3000, or it's got an OH absorption above 3400. So that's a normal alcohol. So which could the 3 lines belong to? Spectrum number 1, that's just a C double bond of number 1. So it would be a ketone, right? Yeah, it can't be a carboxylic acid, it can't be an alcohol. The next one, it's B, right? So because this one is a carboxylic acid, so spectrum number 2, that's a carboxylic acid. So it's going to be B. And the last one is a normal alcohol, so that's so it's going to be B. So you can move into the next one. Is this clear?
Yes.
So the structural formula of an ester is given. The ester is boiled with aqueous HCl, which 2 products are formed. So first thing, you would have to draw this. I've got, I mean, this C. I'm going to start with this C. I got a C. Previously, it's got 2 CH3 branches. And then this C has 1 H and an O and then CO. So it's got 1 H, then it's probably going to have a single O. I'm talking about this one, then a CO. The CO is going to be a double bond O. And then it's got 2 CH2s. So it's got a CH2, another CH2, and then there's a CH3 at the end. I can add in the hydrogens, CH2. This has 1 H. I mean, that's why there was a single O over here, because this C had an H, so it only had 1 bond left. 2 CH3s. So it's boiled under HCl, so it will break down. It will hydrolyze. This side will turn into an alcohol. So you got this alcohol. What's the name of the alcohol? It's CH and
Open
OH.
to all.
So that's propane to all, right? And what is this side? That's
Butanoic acid.
that's going to form carboxylic acid. So that's butanoic acid.
B.
So it's going to be B, right? So that's B. The previous one, you've got which volume of 0.4 mole per dm cube sodium hydroxide solution is required to neutralize a solution containing citric acid. So first thing, you have to come up with an equation like what is the ratio of NaOH to citric acid? So we need an equation. Now remember, NaOH will only be able to neutralize one H plus one ion. Because one H plus one from carboxylic acid is going to come in, it's going to react with the OH ion, and they will form water. They'll get neutralized. So one carboxylic acid group will get neutralized by one NaOH. Is that clear?
So will it be 1:4?
How many carboxylic acid groups do you have to begin with? You got another one?
3.
And you got this one as well. That's a carboxylic acid. So how many NaOH do you need? You need 3 of them, right?
3.
So that's your ratio. It's, I mean, you don't have to make the whole.
Sure. The OH.
Remember, the alcohol does not it does not react with bases. The alcohols are the alcohols are really bad acids.
Oh, okay.
They only react with Na, not with NaOH. Okay, and even with Na, they have a redox reaction, not an acid-base reaction. So it's 1:3. So the question is, you got 0.005 moles of citric acid. So we have 0.005 moles of this. So the moles of NaOH would be 3 times that, right? So it's going to be 0.015 moles, right? Is that clear? Is this clear?
Yes.
So we got 0.015 moles. So now we have the moles. What is moles? Moles is volume, concentration times volume, right? So we have the moles, it's 0.015. We have the concentration of the NaOH as well. That's 0.4 mole per dm cube. So now we can find the volume now. What volume do we have? What is 0.015 divided by 0.4?
.037.
And multiply that by 1,000 because we need the answer in cm cube. So that's going to be C, right?
37.5.
Okay. So that's C. Clear? Is this clear?
Yes, sir.
As the next one, we've got a reduction of compound R with LLH4 gives the compound 4-methyl pentane 2,3-diol. What could be the identity of compound R? So that's reduction. So we basically, the oxidation part, we basically asking you to oxidize it. Carboxylic acid get reduced to alcohols, ketones, aldehydes. They also get reduced to alcohols. So he's looking for the original product. What's the original product? So first thing, first we have to draw this 4-methyl pentane.
So your voice is lagging.
Is this clear now?
It is for me.
Okay. Rizwan, check your end. Okay. As a pentane 2,3-diol. So this is 2, and we've got a diol at 3, and 4-methyl. So what's 4 now? 4 is going to be this one. So 3 H's, 1H, 1H, and 3 H's with this one. So we've got 2 secondary alcohols, right? 2,3-diol. So what could be the only possible product? There would be ketones, right? So I mean, it's secondary alcohol, so it will turn into a ketone. So these are going to be ketones. So I'm going to get rid of the H, put a double bond there. They would actually be ketones. So if they are ketones, which one is the correct option?
A.
This is A, right? So it's A. It's
I didn't get it. Can you just re-explain?
He's saying that there's an alcohol getting formed when reduction happened, right? So the alcohol got formed when reduction happened. So what is the original product? The original product would either be a ketone, would either be an aldehyde, or would either be oxidized to a carboxylic acid, because these will turn into an alcohol. Do you get that point?
Yeah.
So if you're looking for the original product, oxidize the alcohol back again, do the reverse. Right? He said that LiLH4 was added and the alcohol got formed. So if you want to find the original product, you oxidize it back. So we just did that. We had the original molecule, which was pentane 2,3-diol. So you had OH groups on both sides. So what was the original product from which this was formed? So you oxidize
There
it
was
back.
a primary alcohol. Both of them were secondary alcohol, right?
So the original product must be a ketone, because if you reduce it with LiLH4, you'll get this molecule. You'll get this. As a next one, you got a ketone. It reacts with HCN to form an organic product called a cyanohydrin. Which statement are correct? So it's 2 carbon atoms. There's a cedral bond over in the middle and 2 carbon atoms. Now this is nucleophilic addition. What happens is that CN gets added over here, and the top one becomes an OH. The double bond goes away in the middle. And the mechanism is this one. They'll probably have questions on this. The CN attacks the carbon with the double bond and joins with it. The oxygen becomes negative, and then it joins with the H+1. So that's what's happening. Which statement is correct? Does it have a chiral center? It doesn't, because both sides are they're exactly the same. The product is formed from electrophilic addition, which is not true. It's nucleophilic addition. The cyanohydrin product formed by an intermediate which contains a COH group. That's also not true, because the intermediate in this case does not have an OH group. The OH group is formed right at the end. So the only one left is the formation of cyanohydrin product requires the use of cyanide ion as a catalyst. And that is going to be true, because the starting point is that you add NaCN as a catalyst, which provides the CN ions, which attacks the carbon with the positive charge, partial positive charge. Because that's the last statement is true.
So,
Yes.
so KCN can be used as catalyst?
NaCN, remember Na and K are kind of the same thing. Anything that happens with like NaCl would also happen with KCl, NaCN, KCN. So Na is just a spectator and it's not doing anything. As alcohol, Y gives a yellow precipitate with iodoform test. So there's an alcohol that is having an iodoform test positive. So when you have an iodoform test, when you have 2 structures, one is
Carbonate.
one of them is this one. I mean, these are the 2 structures. It's either going to be a methyl with a cedral bond O carbonyl group, or a methyl with CHOH. But since he told us that it's an alcohol, so we're going to go with this one. So our molecule has this structure. And it can be oxidized to give a mixture of products, including substance Z. Substance Z gives a red-brown precipitate with Felling. So what is substance Z?
Aldehyde.
So that is an aldehyde, because aldehydes, they get oxidized with Felling to give a brick red precipitate, and they turn into carboxylic acid. So this one is, it can be oxidized to give a mixture of products, including substance Z. So which alcohol can be oxidized to form an aldehyde? Primary alcohol. So you need a primary alcohol as well. So which one is the correct option? First thing, this one will give a positive iodoform test because it's got CH3 with CHOH, right? The first part. This one will also give a positive iodoform test. You got a CH3, CHOH, right? This one does not have a CH3 with CHOH. It doesn't. This one also doesn't have a CH3 with CHOH. It doesn't, right? Is that clear? So that eliminates B and D, sorry. Now you're left with A and C.
It's going to be A since it has a primary alcohol.
So it's got a primary alcohol because it's supposed to form an aldehyde. It can be oxidized to give a mixture of products. A mixture of product is formed by a primary alcohol. Because a primary alcohol turns into an
But
aldehyde.
also, why are we not looking for an aldehyde instead? And why are we looking for a primary alcohol?
Because the options don't have an aldehyde. I mean, none of the options have an aldehyde. Ajni, what about, so B also has a primary alcohol.
But it doesn't have CH3CHOH, right?
Sorry, we already eliminated B. Okay, that's gone. We already eliminated that. So the only option left is A. I mean, we were basically competing between A and C. So that was a secondary alcohol. So is that clear? A is the option. So now the next one is question 24. When an organic compound Q is treated with the phosphorus PCl5, fumes of hydrogen chloride are evolved. When Q is bound with acetyl potassium dichromate 6, the solution turns green. So there's an organic compound which is reacting with PCl5. So who has a reaction with PCl5?
Alcohol.
Carboxylic acid.
Yes, carboxylic acids do have reactions, but that's in A2. So we're going to go with alcohols. Alcohols have a reaction with PCl5. This one. Where's the alcohol? This part. With alcohols with PCl5, HCl, etc., they will have a vigorous halogenoalkanes will be formed at the end. So alcohols will have a reaction. The carboxylic acids do have a reaction, but that's not in your course at the moment. So we can ignore that. So C and D. It's formed with dichromate 6, the solution turns green. So which one of the two will get oxidized with potassium dichromate 6? This is an alcohol, this is also an alcohol.
D.
C.
What type of alcohol is D?
Primary alcohol.
D is a tertiary alcohol. It's
Tertiary.
C with 3 CH3s, right?
So it does not get oxidized.
Yeah, it has no oxidation. So that's wrong. You're left with C then. That's a secondary alcohol. This one. Is that clear?
Yes.
That's a 23 pe. There's 2-bromo, 2-methyl propane reacts with the NaOH, aqueous NaOH. An alcohol is formed. Which diagram represents the first step of this reaction mechanism? Is it SN1, SN2? What type of halogen? First thing, what type of halogenoalkane is this? Primary, secondary, tertiary. It's propane.
Secondary, tertiary.
Second one, 2-bromo and 2-methyl. So that is a tertiary halogenoalkane. What type of mechanism do tertiary halogenoalkanes have?
One.
Okay, that's SN1. Basically, it's this one that it's this one, SN1. The Cl breaks off first, carbocations are formed, and then the OH comes in. So it's an SN1 mechanism that we are dealing with. So which is the correct option?
B.
Okay, that's B. This one is for SN2, that's for primary halogenoalkane. Next one, structural and stereoisomerism should both be considered. You have to consider both of them. A colorless liquid, see if this thing exists as a mixture of two optical isomers. Okay, fine. When heated with NaOH and ethanol, a mixture of only two alkenes is formed. Now, this is a pretty tough question. It's what could be the colorless liquid? Starting with the first one, I mean, I guess trial and error is the way to go for this one. The first one, it's CHCl, I mean the end part, and it's got two ethyl branches, CH2, CH3, and CH2 and CH3, right? And it's got an H over here. First thing, he's saying that a colorless liquid exists as a mixture of two optical isomers. Is this forming optical isomers?
No.
Yes, it is.
No.
No, it's not.
Yes.
It's not.
It has a chiral
No, it doesn't. It's got two ethyl chains. Two sides are the same. Is that clear? It's not forming chiral. It doesn't have a chiral carbon. Is that clear?
Sir, can you re-explain the question?
The question, I mean, I'm just talking about the first statement. He's saying that the molecule exists as a mixture of two optical isomers. So I took the first one. It's not existing as two optical isomers. Is that clear? I mean, only this part. He's saying that he's basically asking you to figure out what this is. So this one is not the molecule that he's describing. It's not forming two optical isomers. Is that clear?
Yes.
So one second. So the next one, let's try the next one. Is the next one forming a chiral? It's got 5 carbon atoms in the straight. That's 1, 2.
Yeah,
Okay,
there's a carbon with a ClH, CH3, and
okay. So it is chiral, right? So it's got 3 H's. It's got an H over here. It's got CH2 and CH2 and CH3. So this statement is correct, right? So it is chiral. So that's a candidate for this. Let's move to the next one. It's heated with NaOH in ethanol. What happens when you have, they've already told you it forms 2 alkenes. So, and only 2 alkenes are formed. So how many alkenes would be formed when you have elimination for this? The Cl will be lost. A double bond would exist over here, or it will exist on this side, right? So how many alkenes would be formed?
2 alkenes.
It's going to form 3 alkenes.
It could be either 1 and 2, right?
The double bond would either be on this side or it would either be on this side. But there would be 3 alkenes, because if the double bond is over here, you'll have this molecule. The double bond is right at the end. If the double bond appears to be on the other side, if the double bond appears to be on the other side, as if the double bond appears to be on the other side. So these are 2 alkenes that will be formed, right? But this one is going to have cis and trans versions, because the groups around the double bond are different. So it will have cis as well as trans. So this one will have 2 versions. This one will have 1 version. So there's a total of 3 alkenes that are getting formed. Is that clear? Not 2 alkenes, because they've also stated that you have to consider stereoisomerism as well. Is this clear?
Yeah.
Okay, so instead of 2 alkenes, you're actually getting 3 alkenes. The next one. So let's try the next one. Is this, can this be chiral by just looking at it?
no, it's not.
It's not, because the carbon, okay, so the carbon over here has 2 CH3 groups attached to it. So it can't be chiral. So this one is not chiral. You can draw this, but it's not chiral. So the answer is the last one. So we can try and do this one. I've got 2 CH3 branches attached to a carbon. So it's CH3, 2 branches with a C. Then there's another C, which has Cl, and there's another CH3. So this one has H and Cl. I got a CH3 over here. I got a CH3 over here. I've got a CH3 over here, and I've got 1 H over here. Now, that is chiral. That's the answer. That is chiral. This one is chiral. When the Cl is lost, the double bond would either be over here or would either be over here. But there would be no cis trans. Because if the double bond is over here, the carbon has 2 H's. If the double bond is over here, the carbon has 2 CH3s. So when you have the same type of groups on the carbon atom, it's not going to form cis trans. So you'll only have 2 alkenes. The bold and the bold thing, only 2 alkenes are going to be formed. So is this clear? So now the previous one, again this one. Now this paper is kind of pretty lengthy. Structural isoprism only should be considered. So only structural, no stereo. Molecule X contains 3 double bonds. 1 mole of X is reacted with 3 moles of HBr. The carbon skeleton is unchanged. So molecule X contains 1 mole of X is reacted with 3 moles of HBr. How many different products are formed? So that's a tough one. You're reacting HBr, right? So how many different products are going to be formed in this molecule? So the H would either be over here and the Br gets added over here. The HBr gets added to the double bond.
6.
No, we're gonna try and figure out. So I got an H and I got a Br over here, right? I got an H and I got a Br over here. So that's 1. The other option is that the Br could switch positions, right? I mean, the Br and H could switch position. So that's the other option. So here's this molecule. Now the point is, if I switch one side, let me just quickly check. It's 1, 2, 3, 1, 2, 3, 4. So these two sides are different. So the other option, that's 1, right? So we'll keep that as 1. Let's switch these positions. Br gets added over here, H gets added over here. That's my second one, right? I can do it on the other side as well. The Br and H could be switched. So the Br could be on top and the H could be at the bottom, right? That could be another molecule. What else can happen apart from that? So I've drawn 3 of them.
For structural isomer, I think that. Can we swap the middle HBr?
Okay, that's the last thing that we can do. But swapping that, will that change the number of, I mean, will that change the structure of the molecule?
No.
I guess it wouldn't because the molecule is symmetric. Isn't the molecule symmetric? The left and right side, they look exactly the same. Like it's 1, 2, 3, 4, 5. On the 6th carbon atom, you got a double bond. On the other side, it's 1. Is it right in the middle? Just a second. What happened over here? It's 1, 2, 3, 4, 5, 6, right? Over here as well, it's 1, 2, 3, 4, 5, 6. So the two sides, I think, are symmetric. So swapping the middle part will not change the structure of the molecule. Swapping the middle part will not have, if the Br is over here or the H is over here. I mean, this is what I mean by this. Like if I have a symmetric molecule, like I've got a CH3 and I've got a CH3 over here as well. And I'm adding an HBr. So if I add an H and a Br over here, or if I do it the other way around, the Br gets added over here and the H gets added over here, the molecule still remains the same. Is that clear? That it's a symmetric molecule. So I guess I'm going to go with 3. Because the middle part, swapping the middle part will have no effect on the structure of the molecule. Is this clear?
Yes.
Okay, but is this the right answer? That's the question. And then we
The
give
answer is 4.
answer is 4.
B.
4. Yeah, B.
How do you get B now?
So maybe because of like swapping swapping H and Br, it would cause like 2 different values. So 2 would be same and 1 would
The
be.
middle part?
No, so like the either ends I'm talking about.
The either ends were, you had 3 versions, right? You either had Br on top over here and H at the bottom. I mean, the first one that we went for was H at the top, Br at the bottom, right? And H at the top and Br at the bottom. Then we did another one. We swapped one side, right? Br came on top and H was at the bottom, right? So that was our second version. The third version was there are actually 4. Okay, there are actually 4. Because I swapped both of them. So so it's 4 on the sides. Okay, 4 because the middle part does not make an isomer, right? So swapping the middle will not make an isomer. So let me just repeat. It's going to be 4. There's going to be a fourth one as well. So H at the top, Br at the bottom, right? H at the top, Br at the bottom. That's the first version. The second one is swap one side. So Br is on top and H is at the bottom. The third version is swap the other side. This side should remain the same. So I'm going to put it back in the original position, swap the other side now. So that's my third version. The Br is at the top and the H is at the bottom. The third one is swap both of them. Sorry, the fourth one is swap both of them. So that's my fourth one. Okay, that's the one that we missed. So both BRs now are at the top. So I'm just going to repeat this quickly. HBr got added on this side. Swap this side, that's the second version. Keep this side the same, swap the other side, that's the third version. Swap both sides, that's the fourth version. So you're getting four different ways in which the HBr will get added.
Sir, weren't the second and the third isomers the same?
No, they weren't
Because it's a symmetric.
no, neither they weren't the same because once you add HBr, it's no longer symmetric. I mean, once HBr gets added in the middle, though this side has Br, this side has H, so it's not symmetric. So, so there are 4 versions for this. The middle part you can't swap because if you swap it, it's the same thing, but it's just flipped around. I mean, the same 4, but flipped around. Just the same as this one. So the middle part, swapping the middle part will have no effect. So it's going to be 4. Okay. Now question number 20. You've got this reaction with statement, but this reaction is correct. What is this reaction, by the way? I have no idea what this reaction is. You're saying it can be made. This is
addition.
This appears to be hydrofoam. Although whatever this is, it's not part of your course. I mean, what is this thing? This is a carbon with 3 CH3s. You can't even call it hydrofoam. That's definitely not hydrofoam. But anyways, this reaction is not in your course. First part, is it behaving as a Brauch-Lowry base? The first thing, this thing, CH3, 3 CH3, he's talking about this thing. Is it behaving as a base in this reaction?
Yes.
Because it's accepting.
Yes.
It did accept H+1, so that's it. I mean, that's the answer. That's it. Definitely, it does not appear to be behaving as an oxidizing agent because it's not an oxidizing agent is supposed to get reduced. It's not getting reduced. Nothing is happening to it. It's O-1, still O-1. CI bond breaks by homolytic. This is heterolytic. That's wrong. This is hydrolysis. It's definitely not hydrolysis because in hydrolysis, the molecule breaks down into 2 pieces and water is produced. Water is added when you break it down. So this is not hydrolysis.
Sir, how do you know it's hydrolytic fission?
Because the electrons are going in one direction. Homolytic, the electrons are equally broken. I mean, the electrons are equally distributed. One electron goes over here, one electron goes over here. And it ends up in the formation of free radicals.
And in hydrolysis reaction, we have water as a product, right?
Yeah, water is a reactant and water gets added. Like in esters, what happens? Sorry. So in esters, what happens is that the molecule breaks down and water gets added to it, right? That's hydrolysis. So this is no, this is not a reaction with water. That's why it's not hydrolysis. Table describes, now quickly, let's try and finish this off. The organic questions for this paper were kind of tougher. I mean, they were very time consuming. Now, I said, make sure when you're, I mean, there's a quick tip that make sure if you think your paper is lengthy, don't try to attempt isomer questions because they take a lot of time. there's no point in wasting time on one question and missing out on 4 questions. So make sure you try and avoid doing isomer questions if you think you're running out of time. If you have time at the end, you're obviously going to do the isomer questions anyways, but don't prioritize doing them over other questions. I mean, this paper had a lot of Hanji.
So can you utilize your time like by doing inorganic questions first?
Even in organic, most organic questions are very straightforward and very simple. The problem comes with isomer questions. It's very hard to actually even get them right in the first place, and it's very time consuming. Because if you miss just one isomer, that's it. You'll get the whole question wrong. Like we did one question wrong, right? So the point is, if you think you're running out of time, and make sure you divide the time. The first 20 questions are going to take lesser time. The organic questions are going to take a longer time. So don't assume that if you reach the halfway mark, divide the time accordingly. The first inorganic questions and the physical questions are going to take less time. Make sure you're done with them in the first 30 minutes. The next 40 or 45 minutes should be kept for organic questions. They're going to take a longer time. So don't divide the paper equally into halves. The first one should have a smaller length of time. The second half should have a bigger length of time. I said this one, table describes 2 possible environmental consequences of adding too much ammonium nitrate fertilizers, increased plant growths and rivers, that's eutrophication. Does it cause photochemical smog? Who causes
No.
who causes
Carbon monoxide or
Carbon monoxide.
nitrogen oxides.
nitrogen oxide.
Nitrogen oxide, not carbon monoxide. Nitrogen oxides, and they end up forming this compound. What's the name of this compound? Just a second.
PAN.
PN, yes. Which row is correct? Shape ammonia.
So the last MCQ we had wouldn't be producing photochemical smoke.
Which one?
The answer is B, right?
Yeah. Because the fertilizers don't produce, it's car engines that produce photochemical smog, because the nitrogen in the air, it burns up producing oxides of nitrogen, which end up producing PN, which is smog. Which row is correct? Ammonia is pyramidal, right? It's got a lone pair on top.
The ion is tetrahedral.
And that's tetrahedral. That's pyramidal and tetrahedral, and they all have sigma bonds because it's all single bonds, no double bonds in them. H+1 gets added. That's another single bond, dative bond. We've got this one. Z is a compound of sodium, chlorine, and oxygen. It contains 45.1% by mass of oxygen. What do you think this compound is?
Disproportionation reaction, I guess.
Nee, but what is this compound? 45.
NaClO.
It's probably going to be NaClO3. Like I mean, you can do the calculation. Like you can measure 45.1% because that's a lot of oxygen. So it's probably going to be NaClO3. When you get NaClO3, hot NaOH or cold NaOH?
Hot.
Okay, so it's going to be hot NaOH, and the oxidation state would be +5, right? So I mean, you can do the measurement, you can just confirm this, but there was a lot of, like half of the molecule was actually oxygen. So must be NaClO3. Is that clear?
Yes.
The next one is, in a series of 9 experiments to test the reactivity of the halogens, an aqueous solution of each halogen is added to an equal volume of an aqueous solution containing halide ions as shown in the table. So remember, reactivity first thing, increases down the group or up the group?
Up the group?
Down.
Down the group decrease.
The top one is, okay, so down the group it decreases. Top one is more reactive, right? So first thing, we're going to do this first one. There's not going to be any reaction in the first one because Cl2 with NaCl, no reaction. Cl2 with NaBr, will there be displacement?
Yes.
So more reactive displaces, so we'll get Br2 in this one. And Cl2 with iodine, there will be displacement and iodine will get displaced, right? Same thing, bromine with NaCl, no reaction, right? So the bromine will be there, right? Actually, in this one, there's not going to be any reaction, so there'll be chlorine, right? The reason I'm writing bromine over here is because bromine will be added to NaCl. Nothing will happen, so the bromine will be still in the solution. Bromine with NaBr, nothing will happen, no reaction. So the bromine would still be in the solution. Bromine with NaI, will there be a reaction?
Yes. Iodine will get displaced.
So the bromine will go away, it will displace iodine, right? As the next one, you've got iodine, and it will not have any reaction with any one of them. It's the least reactive. So you add iodine, iodine remains. You add iodine, iodine remains. You add iodine to the last one, no reaction, iodine remains. So now let's move to the question. The 9 resulting mixtures are then shaken separately with equal volumes of hexane. So that's an alkane. The 9 tubes are left to stand so that the aqueous and organic solvents separate into layers. Okay. So the aqueous and organic. How many test tubes contain a purple upper hexane there? Let me read the question first.
5.
Achha, who's going to dissolve purple upper layer, right?
Iodine is purple.
Iodine.
So iodine is purple, and that's the iodine
5.
will, so 5, right? So I guess
5.
that's the answer. So it's going to be 5. So 5 test tubes will have iodine in it, and remember, iodine is non-polar. Non-polar things, they mix with non-polar things, hexane. So when you put it in hexane, which it's going to mix with hexane. So the iodine will make it purple. So it's 5. Is this clear?
Yes.
So you can do this. It's I mean, you can try and do this on your own, but what will happen? Magnesium nitrate decomposes. It's going to produce magnesium oxide, 2 NO2s and half O2s, right? So what do we have? A mass of X in these. What's X? A mixture of 2 gases, and they didn't tell us what X and Y are. So here's
Nitrogen and X are not.
X is
NO2.
but
So
they didn't tell what X is. We know that, so X could be O2, it could be NO2, right?
no, but they have mentioned Y is oxygen, so X is going to be NO2.
So they did, where did they mention that? So they did. Yep, they did. So that makes sense. Now, what's the mass of X that is produced? 2 NO2s, right? N is 14, 16 into 3, that's what? 32 plus 14, that's 46 plus, and there are 2 of them, right? So let's assume that 2 NO2s are produced. So that's what's 46 into 2? That's 92 grams, right? And half O2, that's 32 grams into half, that's 16 grams. So I just took the same moles, 2 moles of NO2 being produced and half moles of O2.
How did you find the grams?
Yeah, I just totaled it up. I just assumed that they didn't give us any mass of moles. So they were just looking for the ratio of the masses. So I just assumed that 2 moles of NO2 are produced and half moles of O2 are produced. I just went with the equation. So if 2 moles are produced, what's the mass? Moles multiplied by MR, that's 46 into 2, that's 92 grams. Is that clear?
Yes.
Okay, so what's the ratio? It's going to be 92 ratio 16. What do you get for this?
5.75. It's exactly the A.
It's A, right?
Yes.
So it comes out to be A. Next one is in which all 3 compounds soluble in water. So that's easy. Calcium carbonate is not. Calcium hydroxide is, carbonates are not basically soluble. The last one, this one is soluble. All of them are soluble. Next one is, we've got, remember in the inorganic chart, I've written down the solubility table as well. So go through that as well. And element Y reacts according to the following sequence. Burns in O2, O2 forms a white solid, which reacts with HCl to form a solution, which forms a white precipitate. Who forms a white precipitate with NaOH? Whose hydroxide is insoluble out of all of them?
Magnesium.
Okay, so, and also NaOH is a test for cations. So whose white precipitate dissolves in excess of NaOH as well?
Aluminium.
Okay, because remember the test for cations as well. Let me just. Remember the test for cations. We can, or I'll just simply tell you. Just a second. It's this. So remember, don't ignore the test for cations, even though you haven't done. Most of you have skipped out on your lab, but they do ask you about test for cations somewhere written over here.
So can you please once again share? I just lost this link.
I'll share it. Just a second, man. Somewhere, yes, this one. I said, make sure you memorize all of this as well. I mean, it's they usually do give one MCQ on this. So the first one, aluminium ions, they've got a white.
Have you shared this?
I'll share it right now. Yeah. 1 second. I've shared the board link. So make sure you remember this as well. It's although you haven't done, most of you have skipped out on your labs, but know the test for cations. It's aluminium, that's white precipitate, which is soluble in excess. So he's talking about aluminium basically. That is what the answer is. That's the next one you got. Which one?
Untitled.
Yeah, I didn't get what you're saying.
Why was it aluminium?
Because with NaOH, it gives a white precipitate, which is soluble in excess of NaOH. So according to the test of cations, it's aluminium that gives a white precipitate, which is soluble in excess of NaOH. Is that clear? Because they've given magnesium as well, but it gives a white precipitate, which is insoluble in excess. So the answer is simply, it's test of cations. That's a test for aluminium ions. Is that clear? So anyways, next one is which element requires the least number of moles of oxygen for the complete combustion of 1 mole of its atoms? You can just make a balanced equation for this. So it's probably going to, I mean, you can, yes, it's probably going to be sodium, because if you make an equation with sodium, it forms sodium oxide, right? And if you try to balance it, this has to be doubled and this has to be 4Na. But he's talking about 1 mole of its atoms. So the sodium has to be made 1 mole. So I'm going to divide everything by 4. So this gets divided by 4. This gets divided by 4. So that sodium is 1 mole. So that makes sodium needs a quarter of an oxygen molecule for the reaction. The other ones need a lot of oxygen. Magnesium requires half of the oxygen. If you balance it, it's going to be MgO, and that would require half oxygen. So it's going to be sodium. You can make all the other equations as well. We've got this question. There's a Boltzmann distribution for a particular reaction. The activation energy is X. Which changes to the diagram occurs if an effective catalyst is added at the same temperature? So what happens if you add a catalyst? What will change in this whole distribution?
Activation energy move to left.
The activation energy becomes lower. That's it. The energy of the particles and the distribution of the energy of the particles does not change by adding a catalyst. So only the activation energy decreases. That's it. So which change to the diagram occurs? Yes, the activation energy only decreases. That's it. Now this reaction.
Why not A?
The reason it's not A is the particles, more particles will possess. He's talking about E, this line. This is E, right?
Yeah.
So the number of particles will still be the same. He's saying more particles will possess higher values of E. They won't. It's the same particles. It's only that the E will actually move to the left. There's going to be a new E basically. Is that clear?
Yes.
That new E, the lower activation energy, that's the one that will have more particles, will have energy greater than that. So
All right.
not the old one. It's not going to be for the old one. As anyways, we've got this question, and he's saying that H2 and I2 are mixed together. A mixture containing equal amounts of H2 and I2 is made at temperature T1, and the composition of the mixture is monitored. And a graph shows the results. So this is the mole fraction of I2. So you had 0.5. The experiment is repeated at a lower temperature T2, which graph would be obtained. So now, so the question is simple. The reaction is happening at a lower temperature. Which reaction is favored at a lower temperature, endo or exo?
Exo.
Exo.
So it's going to be exo that's going to be favored, right? So where will the equilibrium shift if it's exo? Forward or backward? I mean, the forward
Backward.
forward is exo.
Forward.
Towards right.
Towards right, right? So we know that if you repeat the experiment at a lower temperature, the equilibrium will shift to the right. So that means what will happen to the mole fraction of I2? Would it be less or would it be more? Would there be more I2 or would it be less I2?
Less I2 at the
Less
same
I2.
time.
Less I2, right? So the mole fraction of I2 would be lesser. So over here, out of 1, if you had 0.23 moles, now you're going to have even lesser. So the point is that the mole fraction of I2 is going to be lesser. So it's P, right? That's the only option here. Can somebody confirm it's P? We just figured out that there's going to be less I2 at equilibrium.
Yes, it's B.
Okay, so it's P. And this is the point where equilibrium reaches, right? Because initially the reaction is happening, but then equilibrium reaches. When equilibrium reaches, the rate of forward and backward reaction becomes equal. So that is when the amount or quantity of I2 will not change. So this is the point where the equilibrium reaches. And over here, the equilibrium is getting reached at this point. It's also slower as well. It's taking a much longer time for the equilibrium to reach. But why is it slower? Because over here, the curve was steeper. Over here, it's taking a longer time for it to reach equilibrium because you're using a lower temperature. So that's another thing that's giving away, that the steepness of the curve is also going to be lesser. It's going to take a longer time, slower reaction. Okay, is the second thing clear as well?
Yes.
So this one, number 9, the zinc ions, which are oxidized by dichromate 6 ions. Chromium is, so we basically have to come up with a balanced equation. Electrons gain and loss, they got to be equal. So Cr is plus 6, Zn is 0, Cr is plus 3, and Zn is plus 2. So Zn goes from 0 to plus 2, so that means it lost 2 electrons. Cr goes from plus 6 to plus 3, so that means it gained 3 electrons, right? So what do I multiply both with?
3 with 2 and 2 with 3.
So I need 2 Crs, right? And I need 3 Zns. So which equation is correct? It's going to be B, right? So you see 3 Zns. And I need 2 Crs. 2 Crs over here, 2 Crs are already over here. Is that clear? So it's going to be C.
Yes.
I don't understand this part.
Whenever you have a reaction, a redox reaction, electrons gain and loss, they got to be equal. Like if I have this reaction, Na is losing just 1 electron. Al is gaining 3 electrons. So how can Al gain 3 electrons when Na is only losing 1 electron? So you multiply Na with 3. Now the number of electrons gained and lost would be equal. I mean, is this clear, this example?
Yes.
So we did.
Then why are we taking Cr to 7 to negative?
What is the oxidation state of Cr over here? That's +6. I mean, you can try and calculate it. It's +6. And what is the oxidation state of Cr over here? That's +3. So Cr goes from +6 to +3. So that's a gain of 3 electrons. Zn is 0, and now it's +2. So Zn is losing how many electrons? 2 electrons, right? So if one of them is gaining 3 electrons, the other one is losing 2 electrons, how can the number of electrons lost and gained become equal? You multiply this by 2, because that would make it 6 electrons, right? So if you have 2 CRs and there are 2 CRs getting produced, so that's a gain of 6 electrons, because 1 CR gains.
So you will have, so you're saying you will multiply 3 electrons by 2. So what,
so we'll multiply.
What is going to happen in the reaction? Like, are you going to place 6 instead of 2?
No, what's happening is 1 CR, what is happening to it? It's going from +6 to +3, right? So it's getting 3 electrons, right? So I need to double that amount. I need to make the number of electrons gained and lost equal, right? So I need to double it, right? How can I double it? I can double the amount of CR. So when I multiply by 2, I'm basically, what I mean by multiplying by 2 is I'll multiply CR by 2. There'll be 2 CRs. But यहाँ पे क्या था?
Make it 4 CR, in part D it will be 4 CR2O7 and 4 CR3 plus.
No, I need 2 CRs. What did I do over here? I multiplied this by 3, right? I made NAs. How many NA did I have? 3 NAs, right? So over here, I'll have 2 CRs. So I already have 2 CRs. And I already have 2 CRs over here. So that's fine. I mean, this equation is fine. And I'll multiply zinc by what? I'll multiply zinc by 3. So I'll have 3 ZNs on both sides. Is that clear?
So why is it not D and C instead? Because you said we already have 2 at both end and D, and we need to.
Sorry. Yeah, sorry. D is exactly the same as well. What's the difference? What's the difference between? No, sorry, D is wrong because D is not even balanced. You got 4 CRs over here. I don't want 4 CRs. I need 2 CRs. Is the point clear? Look at D, it's got 4 CRs. If you have 2 CR2O7, that's 4 CRs. I don't want 4 CRs, I need 2 CRs.
Yes, I get it. Thank you.
So the next one, this is no longer in your course, so leave that. Atomization. As quickly, this one, MC delta T, that's NaOH reacting with HCl, right? So, and the temperature increases by 12. So, and in a second experiment, the same method is used, but 50 cm of 2 mole per dm cube is added to 50 cm of this. What is the increase in temperature in the second experiment? So what is the increase in temperature in the second experiment? So we need to find first thing. Q is equal to MC delta T. What's the mass in the first experiment? (25 cm cube)
25
and 25 cm cube. Total is 50 cm cube, so it's going to be 50 grams. C is 4.18, and delta T is, now this one is another kind of a difficult question. It's what is delta T? The temperature increases by 12, right? So what value do we get for this? Hanji.
So for this, like, shouldn't you find first of all, like, the limiting reactions for this?
No, there is no. It's 1:1. I mean, you obviously know that NaOH and HCl react in 1:1.
2508.
Get that 5?
2508. 2005.
That's the first thing. We don't need to find limiting and excess. Okay, it's the same amount of moles that is getting added, right? And they react in 1:1. Is one clearer? If it's 1:1.
Yes.
So you're getting 2508 joules of energy. So you're getting 2508 joules. What do you think is the amount of heat that's going to be produced in the second experiment without doing any calculations? I mean, you can do calculations, obviously, but look at the moles.
So make T the subject and like make T the subject and then like put
the first thing. Because then that would be 2 unknowns, right? Because you don't know what delta T is. I mean, you can't do MC delta T now. because you don't know what delta T is. You also don't know what Q is, right? In the second experiment. Is that point clear? You can't have two unknowns in the experiment. So by just comparing the reactions, can you figure out Q in the second experiment? Look at the number of moles. The number of moles are doubled. I mean, look at this. This is 50 cm cube of 2 mole per dm cube. This is 25 cm cube. Is that clear that the number of moles of HCl and NaOH have doubled? Is that clear?
Yes, sir.
Yes.
So the amount of energy that's going to be produced in the second experiment is going to be double the amount of the previous one, right? Is that clear? So if the first one was producing 2508, the second one would produce, what's the double of this? That's 25 into 2, that's 50. 16, right? Is that clear?
Yes.
Okay, because you have doubled the moles. You double the moles.
Temperature has increased by 12. So what was the actual temperature?
The temperature has increased by?
Like 12 degrees Celsius.
We don't know what happened in the second experiment.
Right.
And we don't care about the actual temperature because we are interested in delta T. That's it. They're not even, they're talking about the increase or change in temperature, not about what the original temperature is. But is this part clear that in the second experiment, the amount of heat energy produced would be double the amount in the previous one because the moles have doubled? Is that clear?
Yes.
Achha, what's the mass used in the second experiment? 50 cm cube mixed with 50 cm cube. So the solution will have 100 cm. So the mass would be 100 grams. C is 4.18 and delta T is going to be, that's what you're going to find out. So it's going to be 5016 divided by what? Divided by 100 into 4.18. What do we get for this?
12.
So we're getting 12 again. So it's going to be the same energy change as the previous one. Is that clear? And also intuitively, TK, remember this. So why is the temperature, now think about this, why is the temperature change exactly the same, even though the heat energy produces double the amount? Why is the temperature change exactly the same? Like if you produce double the amount of heat energy, the temperature should go up, right? So why is it still the same?
Sir, because the conditions have changed, like.
The quantity of water is different now. If you have a if you have a big bowl of water and you're heating it with twice the amount of energy, it's harder to actually heat it up. If you have a small bowl of water and you're using less energy, so remember this, that although the heat energy doubled, the mass of water also doubled, so it became much harder to heat it up. So but I didn't get what I mean. This one, remember, he's talking about temperature change. Temperature change depends on a lot of things. It depends on the heat energy. It's inversely proportional to the mass as well. If the mass of water is greater, it's going to be harder to heat it up. So the temperature change is going to be lesser. But anyways, hopefully the question is clear. The first one, we figured out that this is the amount of energy that's produced. In the second experiment, because the moles had doubled, so I figured out that the amount of heat would also be doubled. But the mass of water that's being used is also doubled. 50 cm cube multiplied with added to 50 cm cubes, the mass of water is doubled as well. And that resulted in the same delta T. Which shows the greatest deviation? When does an ideal gas deviate? Quickly, last 6 questions. When does it deviate the greatest?
When they have the strong intermolecular forces.
Low temperature, high pressure.
But what about not this one, but when they have stronger intermolecular forces? This one has hydrogen bonding. Which type of interaction exists between water molecules and metal cations in aqueous solution? So what type of attraction exists between a water molecule? I'll draw a water molecule.
Ionic bonds.
Water molecule is extremely polar, right? And I'll draw a sodium ion. What is the type of attraction?
Hydrogen bond.
And now ionic.
This one has a dipole. So this one has a dipole, and this one is an ion. So it's an ion dipole attraction. I mean, it can't be an ionic bond because for an ionic bond you need a negative ion. You don't have a negative ion, so that's wrong. It can't be a hydrogen bond because a positive H needs to be attracted to a lone pair, right? I mean, it's definitely not a hydrogen bond. It's an ion getting attracted to a polar thing. So that's an ion dipole interaction. Is that clear? Not a dipole-dipole interaction because this one doesn't have a dipole. So the other ones are definitely wrong. The only one that fits the description is C. A dipole getting attracted to an ion. As a question number 4, you got krypton and it has X2 plus has the same electronic configuration as krypton. I'm not sure, but krypton I think has 36 electrons. How many electrons would X have? Would X have? Would it have more than krypton or would it have less than krypton? Read the question carefully.
38.
Less than.
No, it's going to have 38 electrons because he said that X2 plus has the same electronic configuration. So when it forms X2 plus, it loses 2 electrons, right? Then it has the same electronic configuration. Is that clear that X has 38 electrons? Right? So you just have to figure out which one has 38 electrons. And my guess is, I guess it's this one. Up till argon, that's 18, 20. 20 plus 10, that's, what's 20 plus 10? That's 30. And 38. Okay, that's the electronic, that's the right one. D is wrong. It also has 38, but you don't have 4D. After 4S, you have 3D. So you don't have 4D actually coming after 4S. So it's going to be B. Which element has the highest 5th ionization energy? The 5th one.
Phosphorus.
5.
It won't be phosphorus because phosphorus, when you're removing electrons, it's in group 5. This is easy, this is easy, this is easy, this is easy. The 5th one is also easy. They're all in the outer shell. So the 5th one would not be the highest for phosphorus. It's probably going to be highest for silicon because silicon has 4 electrons in its outer shell. Sorry, 4 of them, right? So the 5th one would be coming from the inner shell. You remove the first one, second one, third one, 4th one. So easy, 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 easy. The 5th one becomes difficult. Is that clear?
Yes, sir.
Yes.
So the 5th highest one would belong to silicon because you're removing, not silicon actually, it's going to be carbon. Silicon and carbon are in the same group, but carbon is a much smaller atom. So it's going to be more difficult in the case of carbon. Is that clear? I mean, the same reason, but carbon has the same electronic configuration, 2 and 4. 4 in the outside, 2 on the inside. But it's going to be carbon because carbon is smaller in size. And it's got lesser shells. So it's much harder to remove electrons from a smaller atom. Is that clear? Is this clear?
Yes, sir.
So this one, you got 2 grams of ammonium nitrate decomposes to give 0.9 grams of water in a single gas. What is the identity of the gas? So it's producing water. We can find the mole ratio. What's the moles of this? I think is 80. So what's 2 divided by 80? How many moles is this?
0.025.
So this is 0.025 moles. And this is 0.9 grams divided by 18. What do you get for that? It's 0.9 divided by 18. So is that 0.05 moles?
Yes.
So it's 1:2, right? So 1 ammonium nitrate produces 2 molecules of water, right? That's the ratio that we are getting. So what is this other thing now? So what's gone now? The 4 hydrogens are gone. That's part of water now, and 2 oxygens, right? So what is left? You're left with 2 nitrogens, right? And you're left with 1 oxygen as well, right? I mean, that's the only thing, that's the only stuff that's left. 4 hydrogens that become part of the water molecule, 2 oxygens become part of the, so it's going to be N2O. Is that clear?
Yes. Sir.
I said, and then the last one, you have to figure out the AR of neon. So that's I said, now here's a tricky part, and that is that it's how do you figure out AR? It's percentage, fractional percentage into the isotopic mass, right? And you keep summing them up. Now they've played a small trick over here, and that is that they're not taking it out of 100. Because if you look at the total percentage, it's 100 of this, 0.3 of this, and 8 of this. So the total is now actually 108.3. So the first one, the isotope having a mass of 20 multiplied by the percentage abundance, that's 100 out of how much? It's out of 108.3. Is that clear? Okay, that's the fractional percentage. And they didn't even write percentage over here. So that's not the percentage actually. So a lot of people would make the mistake of taking 100 out of 100, right? What's the next one? It has a mass of 21 into fractional percentage, that's 0.3 divided by 108.3. And the third one, that's 22 multiplied by the fractional percentage, that's 8 over 108.3. So what do you get for this? And is this part clear that the total is going to be 108.3? Is that clear?
Yes, it's 20.15.
Okay, so it's coming out to be 20 point, we do have 20.15. Okay, just be very careful about this, that are they giving you percentage or are they not? Because then you would have to calculate the fractional percentage. How much is 100 out of the total, which is 108.3? So be very careful with these questions. But anyways, this was a much lengthier paper and was much trickier as well. So we'll continue tomorrow then.
I do have questions. Should we do them tomorrow or right now?
Tell them we'll do them tomorrow then.
All right, sir. Allah Hafiz.
Okay, take care.